So this is work on non-Hermitian dispersive hydrodynamics. My name is Sathyanarayanan Chandramouli. I'm a PhD student, Department of Mathematics at Florida State University. So I'd like to acknowledge my collaborators. Nicholas Hossie is here with us in the audience. And also Dr. Ziad Muslimani at Florida State University and Dr. Konstantinos Makris at University of Crete. I would also like to take this opportunity to acknowledge some folks who've provided a very supportive environment for me to learn about dispersive hydrodynamics in nonlinear waves. Dr. Mark Hofer, Dr. Patrick Sprenger, Yifeng Mao, and all the other members of the hydrodynamics laboratory. Thank you. So just a brief motivation for the present work. So as we all know, dispersive hydrodynamics is the study of multi-scale nonlinear wave dynamics in fluid-like media with dispersion. Typically, the focus is, and dispersive hydrodynamics has been extensively developed for conservative dynamics in closed systems. However, there have been some interesting offshoots with respect to dispersive dissipative dynamics, of which the KdV-Burgers equation is a canonical model. In this talk, the focus of this talk is going to be on the nonlinear Schrodinger equation, which is a conservative system. Dispersive hydrodynamic phenomena here have usually been observed either via defining a Riemann problem, classical work by Gennady L. and collaborators in 1995 led to the full characterization of the NLS Riemann problem. Also, there's also been work by Mark Hofer and collaborators who studied pistons in the nonlinear Schrodinger optical flow. However, in this talk, we're going to look at hydrodynamic phenomena in driven dissipative or non-Hermitian systems. So here, the aggregate dynamics are subject to gain and loss. So hydrodynamic phenomena have many interesting applications in polariton condensates, smart materials, non-Hermitian acoustics in metamaterials, and etc. And I point to this review paper by Ashida in 2020. However, in this talk, we're going to focus on dispersive hydrodynamics in driven dissipative type systems. There were some nice experiments done by Amo and collaborators in 2009, where they look at the flow of a supersonic polariton condensate over a barrier, and they observe the generation of these Cherenkov waves. There has been extensive theoretical study, particularly done by Kamchatnov and collaborators, where they observe some interesting non-Hermitian interesting phenomena specific to non-Hermitian systems. So just a quick review of what's been done, the classical dispersive hydrodynamics for nonlinear Schrodinger equation. In particular, we look at the defocusing NLS given in equation 1, where psi, the variable psi, denotes the envelope field strength of an optical beam, and t here denotes the propagation distance, which is a time-like variable, while x denotes the transverse variable, the transverse distance, space-like variable. As we all know, with the Madelung transformation, well-known Madelung transformation, we can view the NLS in a hydrodynamic form, given by equations 2 and 3, where we essentially have a hyperbolic shallow water system with dispersive corrections that arise from this quantum pressure term. And so this motivates the study of the Riemann problem, and in particular, I point to the famous shock tube problem, where we have two nonlinear Schrodinger plane waves connected via a sharp transition. And the analogy is with gas dynamics. So here, it's called as the shock tube problem, where we have a diaphragm that separates two optical fluids initially at rest, and the diaphragm is removed instantaneously, and there is a tendency for the hydrodynamic pressure to be equalized, which results in the generation of nonlinear waves across the barrier. However, in this talk, we are interested in non-Hermitian dispersive hydrodynamics. Specifically, we are interested in optical waveguides with external gain-loss distributions. So we have the potential term here, where the real part of the potential denotes the refractive index of the inhomogeneous medium, while the imaginary part denotes the gain-loss, the spatial gain-loss distribution. And these gain-loss regions can also be engineered using several techniques. For example, see this paper in 2017. As usual, we can employ the Madelung transformation, and we obtain the following dispersive hydrodynamic equations, where in particular, we have now a source for the hydrodynamic mass, which arises from the gain-loss distribution. And besides, we have an additional source for momentum generation, besides the usual term. And for the rest of the talk, we are going to be focusing on a very specific example of optical one waveguide with a very simple gain-loss distribution. So there is a region of gain and a region of loss, which are symmetric. Okay? So we have a PT symmetric potential in this case. And of course, one can also view the dispersion-less hydrodynamic approximation, where we have the usual Riemann invariance and hyperbolic speeds. But of course, we now have source terms, one which is gradient term, which arises from the refractive index distribution, while the other arises from the gain-loss distribution. And of course, I acknowledge the scaling here. So in the scaling of x goes to epsilon x, t goes to epsilon t. For slowly varying index of refraction, slowly varying gain-loss distribution, which is weak, we examine this hydrodynamic approximation. In particular, we are going to be focusing on these very special Vedati potentials introduced by Vedati in 2008. I'd like to point out that these possess several exceptional properties, which usually are restricted to only conservative Hermitian systems. So here, the refractive index and the gain-loss distribution have a very specific form given by w squared by 2 and w prime by 2, where w itself is the derivative of a chirped face. Okay. In particular, an important property of the Vedati potentials is that they possess stationary modes of the form given here. And these stationary modes exist as continuous families, which is remarkable for a dissipative system. And it's thanks to this transverse conservation law that these Vedati modes obey. And one could have different density distributions. The density distributions could either be localized or kink type. Furthermore, one could also possess constant density modes. So modes whose density is constant across the transverse coordinate, in which case we see that when the hydrodynamic velocity distribution is equal to the Vedati forcing velocity, we could have a possible solution. So I've shown that here in figure 7, a kink type Vedati mode in red, while a constant intensity Vedati mode plotted against it in blue dashed. Specifically, now, the dispersive hydrodynamic equations reduced to this forced system given by equations 16 and 17. And I'd like to point out that this system generalizes the usual dispersive Euler equation system. And to see that, we consider the case of linear phase distribution, in which case it goes back to the dispersive Euler equation system. So, as I said before, we have the stationary modes of constant intensity, and for this specific one PT symmetric one waveguide example, we published a paper recently where we showed that they possess these topological constant intensity waves. So here in figure 2, I've shown the real and imaginary parts of the solution. So they have constant intensity, while they have a phase jump of pi/2 across the potential. And for a general chirped phase, we have the constant intensity solution given in equation 20. And like before, these generalized nonlinear Schrodinger plane waves with linear phases. And there's a lot of literature for the experimental realization of these constant intensity waves, both in non-Hermitian acoustics and as well as in two-dimensional photonics. So just quickly summarizing, we have these constant intensity waves central to what we're working on. And I'd like to point out that they're generalized NLS plane waves with linear phases. They are a one-parameter family of solutions, and they're characterized by the same chirped phase distribution, theta. So, and I'd like to point out that this chirped phase can be any smooth function. And finally, these constant intensity waves do not exist in generic, either Hermitian or non-Hermitian, inhomogeneous media. And they are unique to Vadati potentials in 1+1 dimensions. And they persist in 1+2 dimensions as well. And finally, these Vadati potentials do not have to be PT symmetric. So all that we're doing is extendable. So now that we have defined constant intensity waves, one can now study modulational instability of these constant intensity waves and look at pattern formation. So for the first time, this modulational stability of constant intensity waves in a periodic potential or a waveguide array was done by Macris and collaborators in 2016. And recently, there was a scheme to realize optical wave formation due to modulational instability in a Rydberg gas, very recently published in 2022. So in this talk, we are interested in these localized potentials, these optical one waveguides. So we examine modulational instability of these topological constant intensity waves in this waveguide. And because here, these constant intensity waves are envisioned to be a fundamental ingredient to the study of dispersive hydrodynamics, much like plane waves are in nonlinear Schrodinger equation. So we perturb these constant intensity waves with disturbances given by epsilon. And we can define an eigenvalue problem, a stability problem, given by equation 25 with the stability matrix, where the hydrodynamic forcing now enters the stability problem. And for a wide range of potentials, one can use this method, Floquet-Fourier-Hill, developed by Deconic and Koods in 2006. So unlike NLS, the density rho naught is now a bifurcation parameter. Yet another bifurcation parameter is the relative strength of the gain loss distribution, with respect to the index of refraction of the inhomogeneous media. So we look at the bifurcation problem associated with beta, the relative strength. So we examine the stability spectra for beta equal to pi/2, 2, and 2.5. And initially, we see the stability spectrum is purely real. So we have stable constant intensity waves. And then at roughly around 2, we observe the emergence of complex quartets or instability, modulational instability. And what we're looking at here are the dynamics of a modulationally unstable wave perturbed by some small amplitude noise. And in long time, we observe the formation of these Vedati modes, which connect to the external flow via dispersive shock waves. And here we show that we verified that these are indeed, so we numerically through a boundary value problem computed these solutions and verified that what we see in the initial value problem is indeed a Vedati mode, localized Vedati mode. So to summarize, we have tested a broad class of potentials for which constant intensity waves are stable in some parametric regime. We've tested 2 bifurcation parameters, rho naught and beta. Rho naught is the intensity of the wave, beta is the relative strength of the gain loss distribution to the index of refraction. And upon symmetry breaking, complex eigenvalues occur in quartets, which is known. And then we also observe symmetry breaking with increasing values of beta and decreasing values of rho naught, typically. And so the dynamics of these perturbed unstable CI waves typically leads to these Vedati modes. And the stability of these Vedati modes is to be investigated. We point to the shedding of dark solitons at the lossy arms. And counter-propagating dispersive shock waves to connect with the external flow. So having now examined this fundamental ingredient of non-Hermitian dispersive hydrodynamics, we can now begin to look at wave breaking in these non-Hermitian media in a fundamental sense. So in particular here, we point out the difference between what we see in classical NLS versus what we see in the non-Hermitian NLS. In particular, we take a Gaussian pulse on a constant intensity background of density 1, and a Gaussian pulse that's centered towards the region of gain on the same constant intensity background. And we observe very different times for wave breaking as compared to for nonlinear Schrodinger. And also, we observe different dynamics for when the pulse was either centered or skewed towards the region of gain. So typical of a system where we've lost space translational invariance. So now we can define a Riemann problem in for this non-constant coefficient partial differential equation given in 31 with the real and imaginary parts of the potential defined via this chirped phase. So the idea is to connect 2 distinct constant intensity waves supported by the same non-Hermitian waveguide, as we have in equation 34. So we have 2 distinct constant intensity waves with different intensities, but they have to be supported by the same waveguide, so they have the same chirped phase. And we point to how we now have a 3-parameter family of non-centered Riemann problems for a given Vedati potential. So our 3 parameters now are x naught, which is the relative location of the Riemann step with the gain loss region, and these 2 hydrodynamic densities. And this is particularly because of loss of reflection symmetry and loss of space translational invariance. Okay, And for the equivalent hydrodynamic system, these are our initial conditions. So we have two initial densities across the step, while the hydrodynamic velocity is in general equal to the phase gradient, the chirped phase gradient. So we now examine the degenerate problem where x naught is equal to 0. We've centered the step at 0, while the right density is identically 0. So looking at some initial value computations. So we observe two families of nonlinear waves connected by this Vedati-kink mode. So in B, I show the development of this Vedati-kink mode. So we have some initial amplification at the region of gain, leading to this bump in the density, and the eventual trapping of this Vedati mode. And in this figure, I verify that this is indeed a solution to the non-Hermitian NLS with Vedati potential, where I've computed through a boundary value problem the density and the velocity of the kink structure. And in particular, I'd like to point out the velocity profile plotted against the hydrodynamic forcing in blue dashed. One can now examine a series of Riemann problems for different left densities. And as the left density increases, we observe the disappearance of the dispersive shock wave with just dispersive radiation. And then across an even larger left density, we observe two rarefaction waves. We can now examine what happens when the step is reflected, because now we've lost reflection symmetry. So there's this unsteady intermediate feature that's formed, and dark solitons that are emitted across. So this is a zoom-in view showing the dynamics. One last result. So this is just to depict the loss of space translational symmetry. So in this case, we've shifted the step away from 0 at negative 200. We have this initial flow which hits the potential. We have the formation of this Vedati mode on a slowly varying background of the rarefaction wave. And then we get this oscillatory wave train just ahead. So there are more intricate results, which I will not go into. So just looking at some applicable lessons for our current work, this is just, these are a few things we've realized recently. So there are several things to be learned from, as I understand now, there are several things to be learned from the transcritical flow problem, past an obstacle, wherein the flow speed is nearly equal to the linear long wave speed. And there have been several works by Gennady and collaborators, and Les Sin and collaborators in 2009, and in very different realms, in the realms of BECs and shallow water flow past variable topography. And here in particular, I'd like to point out these very similar hydraulic transitions between upstream and downstream flows, which we observe in some of our numerical computations as well. In our case, instead, we observe these Vadathi mode transitions in the Riemann problem. And so to study this, which we're doing right now, we need to appropriately scale. So we have a slowly varying potential with a weak gain loss distribution, which itself is slowly varying. And we can do this by picking a very specific phase function whose derivative is slowly varying, but which leads to fast oscillations. So summary, so we've proposed to study a very special non-Hermitian dispersive hydrodynamic system. This is a variable coefficient PDE that supports constant intensity modes. And this allows us to define a Riemann problem which connects two constant amplitude states, each of which is supported by the non-Hermitian waveguide. We've identified modulationally stable constant intensity waves, and from which we've looked at the non-Hermitian, non-centered Riemann problem. So we observe steady intermediate features and unsteady intermediate features. The transition from steady to unsteady intermediate features, as I understand, is an interesting problem. Characterizing the hydraulic limit needs to be done, and also studying the problem for short-range potentials, which was done in a different context. So that's all I had. Thank you for your attention.
Thank you very much. Are there any questions?
Thank you. I thought it was a very interesting idea to try the Vadathi potentials for DSWs and related concepts. So the question that I have is maybe a conceptual one. And it's whether we should really call this modulational instability in the following sense. From the point of view of this is the stability of a flat state, we call it modulation instability. But from the point of view of, do you have like a band of eigenvalues going out, and are the eigenvectors extended versus potentially localized? Is that MI? So in a sense, like when you look at the eigenvector of your instability, is it perhaps a localized eigenvector around the change from positive to negative or not? And also, if you increase the strength of your gain and loss, will you get like a band of eigenvalues, or is it an isolated eigenvalue which is giving you that quartet, and that's it?
Oh yes, yes. These are isolated eigenvalues that we. But of course, in the periodic case, we obtain like bands of unstable. We obtain spectral bands.
Can you show equations?
Yes.
I'm just wondering if analysis can be simplified by some simple transformation, like your function multiplied by exponent. Yeah, here. If you make transformation, psi is whatever, some other function, and exponent I theta with some coefficient. So I think you can kill potential, and you will have just first derivative in x with some inhomogeneous function. Yes. Can it help?
Yes, definitely. Like you mean, so if we define psi as phi E I theta, and then we end up getting rid of the potential, but we get I W psi. Yes. Yes.
With some I, and then double first derivative of phase. So this potential can be removed completely.
Yes.
But you will have some moving framework. I'm not sure how to describe it correctly, but you will have basically a W function. And first derivative on x. Can this help analysis or simplify?
Definitely. I think I was fiddling around with some like deriving the perturbed Widom equations on that modified PDE. So where we get rid of the potential, but we have this like this group velocity like term.
So you cannot remove it probably
Yes.
because it is x dependent.
Yes.
But it is still something in the spirit of moving framework, right?
Yes. 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 Thank you.
Okay, well, we transition. Is there another question possibly? Yeah, go ahead. Yeah, we can go ahead and set up the.
This was about the last slide, the last that was shown. No, but it's okay. Indeed, it seems to make sense that to make a small, a delta peak approximation of your strange potential, concerning the fact that you look at structures of extent which are large compared to the one of the potential.
Yes.
And so, and my question is that, can these type of potential represent defects in a waveguide or something like that?
I think so, yes. But what's not clear to me is the impurity explains the waveguide, but I'm not clear on what the gain loss distribution, because the gain loss distribution would be like delta prime. So I'm not sure what that would be physically. But it could be a useful tool, I think. So.
Okay, thank you very much. Let's thank the speaker again. So our next speaker is Raphael Stuhlmeier, sorry, from University of Plymouth University, and he's going to talk about Hamiltonian dynamics of degenerate quartets of deep waterways.
Thank you, Henrik.